Hi everyone and a very good day. We are from Group T, the company name of Nitric Hub, here today to explain on our material balance project which is on the production of nitric acid.
So next we will talk about on content. First it will be on about us, and the next one is introduction, and then material safety data sheet, and continue with block flow diagram and the conclusion. And now we have our group members here. First and foremost, it is Kritesham, and his metric number is 225380. And next is me, Sharmila Parmasivam, and my metric number is 224559. And the next is Iman Shakir, and his metric number is 222706. And lastly is Unku Nur Atia Sajida, and her metric number is 224647.
For the introductory part of our project, Nitric Hub is a company that aims to produce nitric acid. So I think most people will know this. Nitric acid is one of the main chemicals used in various fields of chemicals and even engineering. Even though nitric acid has its own disadvantages, such as its high corrosive nature and can dissolve materials of metals and non-metal easily, it is also advantages in various fields such as fertilization production, metal cleaning, and even electronics. So this project is used to study of production of nitric acid while using anhydrous ammonia as our feed material. The oxidation method that we use is based on the Oswald process, which offers several advantages for the production of nitric acid, such as high yield will be produced, which means high amount of production of nitric acid is possible from this method. Moreover, this method also provides flexibility for us with the reaction conditions to produce the optimized yield selectivity and even minimize the undesired byproducts.
This is the MSDS of NH2, which is anhydrous ammonia, which consists of precaution, prevention, and hazard.
So this is the material safety data sheet for water.
This is the list of MSDS for hydrogen.
This is the material safety data sheet for oxygen.
So this is the material safety data sheet for nitric oxide. In this slide we can see the prevention, precaution, and also the hazards for nitric oxide. And this is the material safety data sheet for nitrogen dioxide, NO2. And in this slide we can see the prevention, precaution, and hazards for nitrogen dioxide.
Here we have the material safety data sheet for nitrogen. And finally, here's the material safety data sheet for nitric acid. Now, we'll be talking on our block flow diagram. Every single group member of Nitric Hub will be explaining in deeper on their block flow diagram. But for now, I'll be just giving a brief overlay on our block flow diagram. So as you can see in our block flow diagram, our feed material anhydrous ammonia enters into reactor 1, and our final product, which is nitric acid, leaves from our final component, which is evaporator. In total, there are 7 units in our block flow diagram, which is essential in producing strong 95% nitric acid.
In reactor 1, an anhydrous ammonia will react with oxygen and nitrogen to produce a desired and undesired product, which is nitric oxide and also nitrogen gas. So there will be 2 equations. One is desired and another one is undesired. And we have a selectivity of equation 1 over equation 2, which is 0.35, and we have the conversion, which is 22.4%. Ammonia will convert to nitrogen oxide, and the reactor will be on the temperature of 800 Celsius and the pressure of 1.6 atm. And in reactor 1, there will be 3 inputs, which are ammonia, oxygen, and nitrogen gas, and the output will be 5, which is nitrogen, ammonia, oxygen, water, and nitric oxide.
So for flash column, the intent is to separate between condensable NH3 and H2O and uncondensable O2, NO, and N2 gas from the feed. The value of the input has been taken from reactor 1 output with the temperature of 86.02 degrees Celsius and pressure of 5.922 atm. The condensable NH3 and H2O gas has been turned into liquid form. So by this, the liquid and gas form has been separated with the mole rate of 52.49 kilomoles per hour. NH3 and H2O has been taken out from our production. However, for O2 and NO and N2, with the mole rate of 50.04 kilomoles per hour, have been taken to reactor 2 for the next reaction to happen. Separator 1s of 25 degrees Celsius and 1 atm pressure have reached the goal for separating nitrogen and oxygen gas into one stream and nitric oxide into another stream. Nitric oxide will be taken to reactor 2 for further reaction, while nitrogen and oxygen gas will be taken out from our production.
Separator 2, the intent is to separate the N2 and O2 gas, which in the input is 1 kmol per kmol of air, and then there are two different output stream, which is on the first stream is 0.79 kmol per kmol of N2 and the other stream is 0.21 kmol per kmol of O2. For reactor 2, the intent of the design is to maximize the amount of nitrogen dioxide produced from nitric oxide. So how I found reactor 2 value is on the input, there is two input, which is from separator 1 and separator 2. From separator 1 is 1 kmol per kmol of NO, and also from separator 2, 1 kmol per kmol of O2. How I found the value on the output is by using NO conversion, which is I found the amount of NO on the output, and then when the oxygen that are on the input will be same on the output because it doesn't react, it just acts as an oxidant. So I found the kmol per kmol of O2 by dividing the value of O2 and also the value of total of all the mole per hour in the reactor 2. So how I found for the NO2 is by minus all the total amount of output in the reactor 2 minus by the oxygen value and also the NO value. So I get the value and then I divide it by the total value to get the kmol per kmol, which is the mole fraction.
Now, I'll be talking about the block that I have designed, which is the absorption column. The intent of the absorption column is to react nitrogen dioxide with water to produce nitric acid. So the absorption column is at a temperature of 300 Celsius and a pressure of 8 atm. There are 4 streams in this absorption column. The first stream is stream 11, which consists of nitrogen dioxide, oxygen and nitrogen oxide, which comes from the reactor 2. It mixes with a stream of water, which is stream 12, and there are 2 streams leaving, which is stream 13 and stream 14. Stream 13 consists of the nitrogen dioxide, oxygen and nitrogen oxide. Meanwhile, stream 14, which is the last stream for this block, consists of water and nitric acid. So as I said before, this happens at temperature of 300 Celsius and 8 atm. The molar flow rates are almost balanced for the input block and output block, and the mass flow rates are equally balanced too. So there are 2 reactions happening in the block flow diagram. The first reaction is 4NO2 plus 2H2O plus O2, we get 4HNO3. Meanwhile, the second reaction is 3NO2 plus H2O plus 2HNO3 plus NO. So basically, I have used extent of reaction method with some other informations to balance out this block diagram for absorption column. Now we have the final block of our process, which is the evaporator. The intent of the evaporator is to remove water and to produce pure concentrated nitric acid. The stream leaving the absorption column, stream 14, which consists of nitric acid and water, enters the evaporator, which consists of 2 streams leaving, which is stream 15 and stream 16. Stream 15 consists of pure nitric acid and a little bit of water. Meanwhile, stream 16 consists of almost all water that has been evaporated from this process. The evaporator happens at a temperature of 217 Celsius and a pressure of 5 atm. From this process of evaporation, we obtain pure concentration nitric acid of 95%.
And lastly, thank you so much for listening to our project presentation. Thank you.